Now let's try and look at two celebrated partial differential equations. Why we say celebrated? Because they find innumerable engineering applications and also physics-based applications, meaning for research also. Of course, when we talk about these equations, the 3D wave equation and the three-dimensional heat equation are of practical significance for many engineering applications. But however, we have simplified the situation here rather. So we are considering only one-dimensional wave equation and one-dimensional heat equation. But that lays a perfect foundation for you to appreciate the three-dimensional heat and wave equations. That gives you an insight as to how we are arriving at the equation. And also, in the futuristic discussion, we will also consider detailed solution to these equations. They are also of practical significance. There can be several situations where the wave and the heat equations can be applied. Now, one of the simplest applications that you can think of as soon as you look at the 1D wave equation is the basic acoustics. Not only that, the wave equation is of great significance whether you are talking about a stress pulse transmission in a structural component, whether you are talking about waves transmission in fluid medium. So everywhere, whether you are talking about quantum mechanics, whether you are talking about engineering applications, the wave equation assumes great significance. Now, how do we actually establish this simple one-dimensional wave equation? Here, we are looking at the transverse vibration of a constrained string. And what we are trying to do here is we are applying the Newton's second law. That is, F is equal to ma to an elemental string. Of course, we are also going to state all the assumptions that we would make when we are going to establish this relationship. But everything incepts with the balance of forces. That means inertia is provided by a part of the tension in the string. And of course, when we talk about 1D wave equation, we are deeming upon string as a 1D object. That means we are considering mass per unit length as the density of the string. So before we take it up, before we apply our strategy of F is equal to ma to derive this equation, let us first try and understand the symbolisms that we follow, the assumptions that we make, and finally we will conclude with important commentary. So let's get started in earnest to derive the wave equation, that is one-dimensional wave equation, and the situation that we are considering is the transverse vibration of a string. Now, before we implement the strategy, that is implement Newton's second law to form the one-dimensional wave equation, it is very important that we understand the incidental symbolisms and also the important assumptions that have to be in place before we start deriving or developing the expression for the wave equation. Now, one of the symbolisms that we are going to stick to is u of x comma t. Why there are two independent variables? Because you can see in the figure that at any x at any time, the displacement, the vertical displacement is changing. So therefore, it is important that the displacement of the string is defined, and it depends on two independent variables x and t, which in fact warrants the use of partial differentiation. So therefore, all the kinematic parameters of u that we are going to define would necessarily have to be partial derivatives, right? So that is very important. Now let's come to the assumptions that we are going to make. The first assumption is that the string is a one-dimensional object, a very light string, and its density is going to be defined as kg per meter. That means if you multiply the density of the string by an elemental length, you will get the mass of that elemental string. That's very important. The second thing, the gravity has no role to play. The gravity has no effect. It's quite it can be realized quite easily, because if you are talking about a very thin string where the tension is the dominating force, gravity has a very small effect, and that is neglected. The third important thing is it is very flexible, so therefore it has no bending resistance whatsoever. The fourth assumption is that the motion is strictly confined to the y direction. That means whenever I am talking about motion along the horizontal direction, there is no motion. The motion is strictly confined to the vertical direction. And also the tension at any point can be found by drawing tangent to the string, because we are talking about a one-dimensional situation. So therefore the tension to the of the string can be got by drawing tangent to the string at any instant. And before we move on to the next step, you can also look at the free body diagram of an elemental part of the string, and you can see how the tensions are indicated. Now let's get started in earnest developing the 1D wave equation. We have all our assumptions in place. We have our symbolisms in place. We also know what exactly to do. First, we are going to consider an elemental string, and to that we are going to apply the Newton's second law. So what we are going to do is we are going to balance forces both in vertical direction as well as in horizontal direction, and once we simplify things, we would have the one-dimensional wave equation perfectly established. So let's get started in earnest. Now let's get started with the derivation in earnest. So before we write the Newton's second law, we'll go by the free body diagram that is sketched for you, and we are considering as an elemental length of the string whose mass also is quite easy to reckon. So now writing the Newton's second law for the equilibrium in the vertical direction, because we made an assumption very categorically that there is no motion along the horizontal direction or x-axis. The motion is confined to the vertical direction. So therefore we have the following equation, that is F is equal to ma, where ma is the inertia of the string and F is the net force that is provided by the tension which goes to balance the inertia. So now if you see, looked at the figure, the vertical component of the tension T1 is T1 into sine beta, and the vertically downward component of T2 is T2 sine alpha, and this difference in the tension in the vertical direction must go to provide the inertia, and the inertia can now be written as mass into acceleration. So how do you actually define the acceleration? Because in the beginning of the discussion we made it very clear that the definition of the displacement is u of x comma t, because it varies both spatially and temporally, that is both with respect to x and t, and therefore if you are defining a kinematic parameter of the displacement u, that is we are talking about the rate of change of velocity or the double rate of change of displacement, we will have to use a partial derivative, right? So that is one thing. And what about mass? Since we are deeming upon the string as a 1D quantity, the mass is simply defined as a density into elemental length. So can I rewrite this expression as density into elemental length dx? This gives me the mass. And when it comes to acceleration, since the displacement is u of x comma t, because it is a function of two independent variables, I can use the second partial of u with respect to time so that I get my acceleration. See, now we have the difference in the tensions in the vertical direction is equal to ma, and that is nothing but density into dx, because it's a linear density. I'm talking about a one-dimensional string. So therefore it is sigma into dx and then multiplied by the second partial of u with respect to t. Is that clear? So now simplifying it further, what exactly I'm looking for? Is the next step obvious, or it has to be deliberated further? So the next step has to be obvious, because if you looked at the following expression, that is T1 sine beta minus T2 sine alpha, which is equal to sigma dx, which gives you the mass, and also is going to be multiplied by the second partial of u with respect to t. Now, if you looked at the sine beta and sine alpha in the figure, it is obvious that it can be related to the slope measured at those points, because the string assumes the shape of a curve, and you can see at those points we can use alpha and beta to define the slope. But what about slope? The slope is first partial derivative of u with respect to x. So therefore, every element in this equation, that is RHS, is already in terms of u and t. The LHS also could be converted in terms of u and x, so that you have the standard one-dimensional wave equation, right? So in order to do that, I need one more basic help. That is, I have to convert both sine beta and sine alpha into tan beta and tan alpha, so that I can express them as the slopes. Because tan beta and tan alpha are the definitions of slopes, because tan of the angle made by the tangent with respect to the x-axis. So therefore, what I would do is I'm going to divide both these sides by a quantity. And what is that? Now, if you looked at the horizontal direction, there is no motion, so therefore the components of the tension must balance each other. So therefore, it is quite obvious that T1 cos beta is equal to T2 cos alpha, and you can call this as T. Now I can use this to divide both sides. If I did that, what I will get? I'll get T1 sine beta minus T2 sine alpha, that divided by t, and that is equal to rho dx by t, and multiplied by the second partial of u with respect to t. So now, since t is T1 cos beta, I can divide the first term by the definition of T1 cos beta, and since it is also equal to T2 cos alpha, I can divide the second term by the definition of T2 cos alpha. Isn't that very, very obvious? And when I did that, I naturally get the definition of slope, because this becomes tan beta, this becomes tan alpha. Observe once again carefully. I am dividing the first term by t, and I am using the definition T1 cos beta, that turns this quantity into tan beta, and I am dividing the second term by t, and I am using the definition T2 cos alpha, that turns this quantity into tan alpha. So both are the definitions of slope. So when I did that, what I will get here is tan beta minus tan alpha, right? So this is the slope at one point, and this is the slope at the second point, and this is clearly equal to rho by t, which we are going to attribute a physical significance, rho by t. Just wait for a while, and of course multiplied by the second partial of u with respect to t, right? And we bring the dx over here. So now I am talking about slopes. What is the definition of slope? Dy by dx. But here, since y is replaced by u, which is a function of both x and t, I need dy by dx to be replaced by the partial of u with respect to x. But this is at x plus delta x, and this is at x. All right. This is at x, and the entire thing divided by dx. Now this has to be understood very, very carefully. Of course, the RHS should not be forgotten. Keep carrying all the components of the equation together. And now what happens here? The difference in the slope measured at x plus delta x and slope measured at x divided by delta dx. If the dx is deemed upon as infinitesimally small quantity, then what you are talking about is the rate of change of slope, because this represents the change. That divided by infinitesimally small x means you are actually talking about rate of change of slope, right? So therefore, you are actually here defining the rate of change of slope, which is equal to sigma by t into second derivative of u with respect to t, second partial derivative. So now, since I am talking about the slope measured at x plus delta x minus slope measured at x divided by dx, and assuming that dx is infinitesimally small, this actually becomes the rate of change of slope. How do you actually find out the derivative? The derivative is found by taking the difference of the function at 2 points which are very mathematically extremely close to each other, and divided by delta x, and as delta x tends to 0 will give you the derivative. But here the functions that we are considering are slopes themselves, and we are taking the difference between the slopes of 2 points which are located in the closest mathematical proximity, and divided by that difference along the x-axis would obviously give you the rate of change of slope. Now, the rate of change of slope is actually given by the second partial of u with respect to x. All right, and that is equal to density by tension, and then you have the second partial of u with respect to t. So this is a very important stage of the equation. We cannot leave the equation in this state because the wave is characterized by the velocity, and it has to be expressed in terms of the velocity. So how do you actually attribute the characteristic of velocity to this? One thing that you can do is seek allegiance to physics and say that it is 1 by velocity square, but otherwise the quickest way to check this is to check the units and dimensions. Now, for example, if I am talking about density here, I am talking about mass per unit length, right? Mass per unit length, where m is the standard symbolism for the mass and L is for the dimension. So since I am talking about mass per unit length, L will have the power -1, m will have the power 1. Now let's also write the dimensions for the tension. The tension is obviously Newton. Newton would actually mean what? Newton is the measure of force, our tension here, which is nothing but mass into acceleration, right? Which we have already used in our discussion. So mass, when I talk about it, is the dimension 1 because there is only one term. And what about acceleration? Acceleration dimensions are L into t power -2 because it is meter per second square. The unit of acceleration is meter per second square because it is rate of change of velocity. Velocity has meter per second, and rate of change of velocity is again divided by time. That means it is meter per second square. Now carry out the simplification. You can clearly see that m would get cancelled. This becomes L square, and t, when it goes to the numerator, it becomes L square by t square. So this can be, if you looked at the unit of this is nothing but 1 by meter per second whole square. Meter per second whole square. So that this clearly means that tension divided by density would obviously give you the velocity square, but here you have density divided by tension, so obviously gives you 1 by the velocity square. Meter per second is the unit of velocity. You can see L power 2 and divided by t power 2, that means a meter per second whole square. And also if you go by the algebraic form for velocity or frequency or anything, it is nothing but the tension or the stiffness divided by inertia. So the equivalence of that is there. Sigma represents the inertia. This represents the tension or the force, or it can be an elastic force, it can be tension. So similarly, sigma is inertia, which represents the effect of mass. So therefore sigma by t in fact, both physically and using units and dimensions, represents 1 by velocity square. And if I represent the velocity by the standard symbolism c, if I represent velocity by standard symbolism c, then this can be replaced by 1 by c square, because you can clearly see that t by rho becomes my velocity. So therefore, I am talking about velocity square. Since I am talking about sigma by t, it becomes 1 by velocity square. So what happens to the equation? The equation finally becomes, so let me write both the equations, that is before putting the definition of velocity and after also, so that it becomes very clear to you. So this is equal to sigma by t, which we have proved to be the velocity. So the second partial of u with respect to t, and now this is going to be 1 by c square. So you can see clearly, note that c is nothing but root of t by sigma. This is also very easy to comprehend from the basic algebraic physics. So t sometimes could even be the elastic force, and of course sigma plays the role of inertia. So force, restoring force by inertia, represents the velocity. Here it is velocity square. And finally, this could further be simplified. You can bring velocity to the LHS also. So this becomes your one-dimensional wave equation. And if you bring c here, you can see that you have this standard form. This is the equation that we have been talking about as one-dimensional wave equation. So it depends on two partials, one of the time, the second partial of u with respect to time, and the second partial of u with respect to x. So sometimes this equation is also represented as follows. It is c square uxx is also equal to utt. So this is also one more form of the standard one-dimensional wave equation. So what did we do to arrive at this particular equation? A very simple one, and you would be able to score a maximum of 7 marks if you understand this. We started with the idea of F is equal to ma, that is Newton's second law of motion, and we very clearly saw from the free body diagram that the difference in tensions in the vertical direction goes to provide this inertia. And since mass can be written as sigma into dx, because we are talking about a one-dimensional string, it is the linear density I am talking about multiplied by the second partial of u with respect to t, which represents the acceleration, of course. And once that is done, what we did, we also looked at the horizontal direction. Since there is no force, the components of tensions in the horizontal direction must balance each other, and therefore we could get T1 cos beta, T2 cos alpha is equal to T, you can see in the figure. And then what we did, we divided both sides by T. And while dividing the first term, we used the definition of T1 cos beta. While dividing the second term, we used the definition T2 cos alpha, so that we could reduce both these terms into difference of slopes. And once you talk about the definition of slope, tan beta goes to define the slope at x plus delta x, and tan alpha goes to define the slope at x. And you can clearly see that the difference in the slope divided by an infinitesimally small length of x goes to define that it is derivative. In fact, we can also write it as limit as delta x tends to 0 if you want further clarity. So this goes to define the derivative. Since you already have a derivative, derivative of derivative gives you the second derivative. That means you are going to get the second partial of u with respect to x. That's what exactly this is all about. And then we had one more term, sigma by t, and we analyzed it using dimensions, and then we proved that the unit of this quantity is 1 by meter per second whole square. Of course, from the algebraic physics, since this represents tension, force, and this represents inertia, that is density, this also should give us the velocity 1 by velocity square, and that's what we proved comprehensively here, because we wrote the dimensions for the density, we wrote dimensions for tension, mass into acceleration, and when we simplified, we could get the dimensions of 1 by velocity square. So therefore, we replaced sigma by t by 1 by c square, and that's what we did towards the end. And then sigma by t was replaced by 1 by c square, where c is root of t by sigma, c is the velocity, and then when we took that to the LHS, we got the standard one-dimensional wave equation, and the alternative representation of the equation is given here. So this is very, very important to see that you're not only utilizing the acceleration, the second partial of u with respect to t, but also the rate of change of slope, that is the second partial of u with respect to x. As you appreciate, the partial derivative comes about because u is a function of both x and t, two independent variables. So therefore, you get the partial, and you can see that we have differentiated u twice with respect to one partial one independent variable here and another independent variable here, and both of them are related by c square, which is the velocity of the wave. So this concludes the important derivation of one-dimensional wave equation. Let's move on and develop a one-dimensional heat equation. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.